What are we going to try to do today? We're going to try to build a common understanding of how to support students in making sense of phenomena, and also build a common understanding of three-dimensional learning. And hopefully we're going to engage, and I'm going to try to engage you in doing a little bit of science. And hopefully I have you take part in discussion. It's going to be pretty much a one-way discussion, except if you ask questions, and it'll be kind of like a fake discussion. But nonetheless, we'll try to make this as interactive as possible. I tend to use the word phenomena a lot, and phenomena tends to be really important to three-dimensional learning. And so let's get clear on what I mean by phenomena. Phenomena are naturally occurring events that happen in the world that are repeatable and can be studied and explained. Some phenomena are repeatable. They happen frequently. Other ones take actually centuries or a long time, but nevertheless, they're phenomena, they're repeatable, they're natural occurring events. So when I use the term phenomena, that's what I mean, a natural occurring event, not something that's phenomenal, which isn't a natural occurring event, right? So there's a little bit of a distinction there. Just want to be clear on how I'm using that particular phrase. So I want you to take just a few minutes, and it'd be great if you could just chat these ideas, some of these thoughts down in the chat window. So just write them down. I want you to write down what's different about teaching and learning today based upon either what's happening in your state or based on the vision of the framework for K-12 science education and its companion document, Science and Engineering for grades 6 to 12. I'm not saying you necessarily know about those. I actually don't know if you do or not, but just if you could just take a few minutes and just jot down what you see different about science education today. And I'm just going to give you 1 minute. I'll pull up my phone just so I can monitor my time when we're doing chatting. So a couple of comments showed up on the chat window. Certainly this last year, technology has become very, very important to us as far as teaching if you taught from home. And certainly, we probably all developed a little bit of more fluency and became a little bit more computer literate. I really like the comment that Jean wrote, or Jen wrote, that says, hopefully we're moving away from students learning about to figuring out. And let's hear we'll learn a little bit more about that in a second or two. And Jean can then come back and see if we responded a little bit to that one. So really what I want you to do right now is I'm going to, if you haven't seen this consensus study, this is a consensus study that came out of the National Academy of Science, or the National Academy of Science, Engineering, and Medicine. And you may know about this organization. It is probably the most prestigious body of scientists in the world. It certainly is the United States. And maybe there's some debate that some other nation has a more prestigious body. I'm sure my colleagues in England would argue that their National Academy is more important, more prestigious, but nonetheless, it's a very prestigious body of scientists. And they basically, for this report to go through, to be a consensus study, it had to get the stamp of those scientists. And so this came out in 2019, so was released actually just before the pandemic hit. in October, I think, of 2019. So what I want us to do is I'm going to put up the screen. I'm not going to read them to you. I think we're all capable of reading quite well. I'm going to have you just read the first one or two. But I want you to stop and think about, and once again, if you like, you can write something into the chat window. I want you to stop and think about, what do these little short conclusions mean for your science teaching? What opportunities do they provide? What challenges do they suggest to you? So I'm just going to go to the first. And if you like, the reason this actually gives you a link, the National Academy released in fall 1928. This little link actually will take you to the document that you can download. It's a free download. You can pay $50 for the book if you want, but you can also download it and read it on your computer screen. And I believe I have to stop sharing and reshare so that you can see that particular screen. Okay, so I think you can see that screen right now. I will make it slightly bigger so you can read it a little bit more easily. And again, we're going to look at the first two conclusions. Actually, all the conclusions are very valuable to read, but we're just going to look at the first two today. And again, if you get a minute, if you could just place some comments on what this means for your science teaching, what challenges does it present, what opportunities does it present, etc. So referring back to the comment that Jen made, that hopefully the world right now is moving more towards kids figuring out rather than kids learning about science. We see actually a call or a conclusion from a consensus report from the National Academy of Science, Engineering and Medicine that says pretty explicitly, engaging students in doing science and in engineering increases their conceptual knowledge of science and engineering, improve their reasoning and problem-solving skills. It's the doing of science and or engineering, which is that figuring out part. It's the doing, because that's what scientists do. They do science, and in the process of doing science, they're figuring out how the world works. And so we're in this, from my perspective, and I'm sure I've been involved in science education longer than everybody that's on this particular video conference or webinar. It's a really important call because we're trying to get back to actually kids engaging in the doing of science rather than learning about science. So I'm going to stop sharing here. And I'm going to go back to my PowerPoint. I don't have my PowerPoint. Wait just a second. I just got to find my PowerPoint. Okay, so there we're back at my PowerPoint. So one of the other really instrumental document that was also a consensus study from the National Academies is the framework for K-12 science education. In it, in many respects, is a vision document. It's based upon, and this document was now released 9 years ago. It was a vision document that said, what is it that children all K through 12 should know and be able to do? And how should we as teachers go about doing it in many respects? So one of the first important principles that comes out of the framework is this idea of focusing on explaining phenomena or designing solutions to problems. Now, when I use the word problems, I'm not referring to problems at the back of the textbook. These are real world problems that are complex and compelling, and that as a nation, as a world, we need to find solutions to. So these are complex problems. They're not textbook problems. Same thing like phenomena are compelling phenomena that exist in our world. So there's this notion of focusing on explaining, making sense, figuring out phenomena. In order to do that, we have to focus on the 3 dimensions of scientific knowledge. And these are the, and I'll talk a little bit about these in a second, but these are organized around disciplinary core ideas, explanatory ideas. These are the big ideas of science. They're focused on the central role of scientific and engineering practices, and the notion also of using cross-cutting concepts, which are also big ideas, but they cut across disciplines, and we'll talk a little bit more about those as well. Another really important emphasis in the framework is this notion of coherence in building and applying ideas across time. Now that's critical. And the reason why is learning complex ideas like how matter interacts to form new things is a very complex idea. And so you're not going to learn about that just in a 6-week period of time. Yeah, as in the past, we might be able to memorize stuff, but it doesn't really mean we can apply and use it. The notion of coherence, building and applying ideas across time, is to support kids so they really develop sophisticated understanding of these important ideas so they can use them to make sense of the world. The other important call that comes from this particular document is the notion that learning science is for all students. It's not a luxury. It's not for the privileged class. Everybody in our nation, in the world, really has to have a fundamental understanding of what science is all about so they can make decisions. You know, it was interesting. One of the I think for me, one of the big lessons of the pandemic was how people don't understand the nature of science. The idea that when something novel occurs, a new phenomena like we just experienced, scientists don't know the answers. They have to figure it out. And while they're figuring it out, they get more data, and what they learn changes. And it was so surprising to me that I would read constantly in the newspaper or on the web, I guess. Not that I don't read a newspaper, I read it on the web, that people were perplexed by why the scientists were changing their ideas. Why were the medical doctors changing their ideas? Well, it's because new information was coming in. And that's such an important lesson for everybody in our nation, all our children to know. So, what is 3-dimensional learning? It's the working together of those 3 dimensions: disciplinary core ideas, cross-cutting concepts, in scientific and engineering practice to focus on explaining phenomena, i.e. figuring out, or designing solutions to problems. And the critical aspect behind that is that it's 3-dimensional learning shifts what happens in the classroom. It changes the classroom from a place where kids are learning about something to kids are actually exploring, examining, and using science ideas to explain how and why phenomena occurred or design solutions. It's the figuring out why phenomena occur. By the way, I did not pay Jen to write that comment in the chat, just to let you know. But anyways, it was really a nice lead in, Jen. Thank you. So this is the difference in what's happening today. You know, I taught chemistry for 8 years. And then I taught science methods for another 25, 30 years. I'm still teaching secondary science methods. And one of the, I always prided myself early on in my career to be really good at trying to explain a concept. I still like to explain concepts, but the goal of science teaching and learning is not for kids to know a bunch of concepts. It's actually to have them be able to explain why various phenomena in our world occur and how to solve problems. Now, to do that, they actually have to use the 3 dimensions. And as they use the 3 dimensions, their understanding of those ideas become richer and more sophisticated, and their ability to explain more actually increases. So 3-dimensional learning is all about figuring out versus learning about. Getting kids to make sense of phenomena and find solutions to problems. In order to do that, they really need to have understanding of some explanatory ideas to apply. And as they use those explanatory ideas, they become richer. And similarly, science and engineering practices help build those explanatory ideas. And we'll explore this idea in a little bit greater focus. Oops. Okay, so what are disciplinary core ideas? Again, remember, there's the 3 dimensions of scientific knowledge or 3-dimensional learning. The first in that 3 dimensions, the first is disciplinary core ideas. I like to think of them as the big ideas of science disciplines. And so you can think of what's a big idea, what's a disciplinary core idea? Well, in physics, actually it's across all the disciplines. In physics, think of energy, right? It's such a core, essential idea of energy, and it's challenging. And it's an idea that actually should develop across the grade levels because it really is a sophisticated idea. There's no way we can just learn about energy when we're just teaching about it for 6 weeks in either middle school or high school. In biology, evolution, adaptation, those are critical big ideas, again, that take time to develop and get richer. So big ideas of the science disciplines, the disciplinary core ideas, are those really big ideas that can develop across time and that we can use to explain phenomena. Gene-environment interaction, force and motion, the structure and properties of matter, those are all those big ideas. And we use those to be able to explain phenomena, solve problems, and learn more when we need to. Then there's these things called cross-cutting concepts. Now, cross-cutting concepts are also big ideas. The difference between cross-cutting concepts and disciplinary core ideas is that in some respects, the cross-cutting concepts are critical to all the discipline. For instance, cause and effect, right? Patterns, structure and function. I'm listing as I go down the side here, I just sort of listed the 7 cross-cutting concepts. These are big ideas, but they're not just true for one discipline, they're actually true for all the disciplines. Systems and systems modeling is such a critical idea that cuts across the disciplines, and yet we hardly spend any time helping kids understand what a system is. We do a little bit of it in our biology teaching, but it's such a powerful idea that we just haven't focused on. So cross-cutting concepts cut across the disciplines, but more importantly, I like this because I think the disciplinary, if you just want to ask me, to me, the disciplinary boundaries are artificial from a historical perspective. What's more important about the cross-cutting concepts is that they're lenses to examine phenomena. So for instance, here I see a very important phenomena that occurs every year, and these are honeybees gathering pollen from a flower. And the question goes on here was, what patterns can I notice? What does this have to do with energy and matter? What structures do the bee have that allows it to gather the pollen? In fact, I never noticed this. I think you can see a little bit of pollen on the part of the bee here at the bottom. So what is it about the structure of a honeybee that allows it to gather the pollen, and then know how to take it back to their beehives. It's quite amazing that bees can find their way back. And they actually know, if you have like 4 or 5 beehives, they actually know how to find which beehive is theirs. So cross-cutting concepts are important in examining phenomena. Then there are scientific and engineering practices. These are the ways of knowing and doing that scientists and engineers use to study the natural world or the design world. We know from our stance on inquiry, we know a lot of these ideas. Asking questions has always been an important part of science teaching, although we've never done it very well. We don't necessarily get kids to ask questions. But there's other things that are actually very new. And even though the framework came out 11 years ago, it's still fairly new. That's developing and using models. Such a critical aspect of what it means to do science, developing a model to give a causal explanation for what's going on. And yet it never was a key part of what science was. We always use someone else's model, right? We all memorize various models, but we never develop them and basically asked ourselves, does my model account for all the evidence that I have? And so the scientific and engineering practices are actually the way in which scientists going about figuring out phenomena, along with the disciplinary core ideas and cross-cutting concepts, because you need those. An important aspect behind these is that anytime you're trying to make sense of any phenomena, although there might be a central practice, they actually all work together. It's not like you can just, at any given time, you're really focusing just on this. Anytime you're developing models, you're always taking into consideration the data that you have. And so these examples, these all work together. So asking questions might lead you to obtaining and evaluating some information, which could lead to planning an investigation, which could lead to analyzing and interpreting data, which could get you to use mathematical and computational thinking, which could could involve you engaging in an argument from evidence, which could lead you to developing models and constructing an explanation. So how do practices differ from inquiry? I always get this question asked, so I put it up on the slide so that I don't get it asked. Is that practices basically extend our earlier efforts in engaging kids on inquiry, because it's getting us to focus on helping them in design investigations. What does it mean to construct a model? And how do we know that all our evidence is being accounted for? So it actually is extending what we know. And the whole goal here is to shift the science classroom from environments where kids are just learning about, there's that learning about again, to explore, examine, and use science ideas to explain how phenomena occur. It's that figuring out process. So here's this is one of my analogies that I like to use to talk about the 3 dimensions. And one of the critical aspects is they work together. So we have to realize that if you're going to make sense of a phenomena, scientific practices are critical, but in and of themselves, you're not going to get any place because you don't have any foundation, any conceptual ideas to build on. And certainly having really rich science ideas is important, but if you don't know how to apply the practices, then you can't figure out something new because you don't know how to design a model to say, does this actually account for everything? And so the 3 dimensions work together to make sense of phenomena and build understanding. And so I like to use this analogy of a rope. So often ropes are made up of various strands, and a strand gives you something. You get some strength out of a strand. But you really get the strength out of a rope when those 3 strands are intertwined. Then you really get a lot of strength in your rope to be able to pull something, lift something, and you don't have to worry about it breaking. The same thing is true with the 3 dimensions of scientific knowledge. They work together to allow children to problem solve, make decisions, explain real world phenomena, and learn more when they need to learn more. This is the last of my little analogies to help you see if you understand three-dimensional learning. And it's a cooking example because I really enjoy cooking. Actually, during the pandemic, I did a lot of cooking, but I've always enjoyed cooking, not just during the pandemic. So you have to stop and think about, what does it take to be able to cook? Well, in order to cook, I certainly need to know a lot of techniques. I know that I need to know how to chop. I need to know how to blend. I need to know how to use different kind of frying pans. And those are all great. But knowing how to chop using various kind of pans doesn't make you a good cook. It's essential to be a good cook, but not necessary, but not the only thing. You need something far more than just those techniques. And you can think of those as the kitchen tools and techniques as the scientific and engineering practices. Then we have our basic ingredients. And having good basic ingredients, core ideas, those are disciplinary core ideas, are certainly critical in making a good meal. I thought I had some vegetables in there. Anyways. So these are critical in making a good meal. You buy a good fish, you get some good pasta, especially if you make your own homemade pasta. It really enhances the food, particularly if you know how to use the tools. But again, you can have some really good ingredients, as you might have the right tools and how to use them, but the meal still doesn't taste great. And the reason why is you're missing the vegetables, the herbs, and the spices that really enhance the flavors. Those are your cross-cutting concepts because they work across all three of these things. If you have all three of these things, then you can put them together and prepare a wonderful meal for everybody. That's the three dimensions. They work together. And I think we've all gone into a restaurant to point out the importance of these cross-cutting concepts, or someone's home, and there is just a little bit too much seasoning. And it just overpowers the rest of the meal. And so knowing how these things all, but if you miss those herbs and those seasonings, the flavor doesn't come out. So seasonings can really enhance the flavors, but too much destroys the meal. So all three of these aspects all work together to really support making a good meal, just like practices, core ideas, and cross-cutting concepts work together to allow people to make sense of phenomena or solve problems. I also like this analogy, by the way, if you want to use it, and to think, because it provides, when you serve someone a good meal, or a bad meal, however you want to call it, you get instant feedback, right? You can tell people around the table, are they enjoying your food? Do they like this meal or not? Same thing is true when you have kids construct a model or construct an explanation, plan an investigation, you get information about that child's knowledge, right? So you get both provide feedback, the products from kids engaging in doing science, a meal, you get this kind of feedback that's really critical in judging where they are. I'm going to just stop there just for 2 seconds. And if you have a question about three-dimensional learning, I just want you to sort of throw it into the chat and I will try to respond to it. I see Jen wrote some comments back to me. It says, haha, my go-to response when you're trying to get folks excited about 3D teaching and learning, Joe, I learned it from you. Thank you, Jen. Any questions on three-dimensional learning? Okay, well, again, we're monitoring the chat. So if a comment comes up, please let me know. I can go in the further depth on any one of these. Okay, so what we're going to do now, the reason I had a pause there is we're actually going to take a look at some phenomena. And it's, if I was doing this face to face, we would be all doing this together. But I'm just going to do it because you're separated from each other as well. So I'm going to sort of try to lead us together. And basically what we're going to do is we're going to say, when I mix stuff together, we're going to try to figure out, how would I know whether a new substance is formed or not, or new substances are formed? So that's what we're going to try to figure out. We're going to look at a phenomena and we're going to try to figure out, did I get some new substances or not? And how do I know? What evidence do I have? So I'm assuming we're all science teachers. And so we actually are coming to this event, or coming to this situation with some prior science ideas, either from earlier in the year or from a previous year, right? So we know at this point that matter is composed of atoms and molecules that are in constant motion. We know that substances can exist as a solid, liquid, and the gaseous state, so all three states. That substances have characteristic properties that I can measure, or that we can measure, and we can help identify that substance and distinguish them from one another. And some of the properties that we know at this time are solubility, density, melting point, and properties. Oh, I just saw a comment from Kevin. Kevin, I'm going to come back to that question. Let me keep going on to this, and I'll come back and answer that because that's a really important question. So we're going to do the Baggy investigation. Hopefully you haven't seen it. I've been doing it for many years nowadays, but I really like it because it's really a nice figuring out process. So what we're going to do is we're going to conduct an investigation. We're going to record some data, and then I'm going to get you to construct a scientific explanation. Again, if we were together, then I'd have us work in teams and collaboratively, but we'll just take a few minutes to do this on our own. I'm going to once again ask you, if you can't see what I'm doing, put it in the chat so that I can then explain, I can be clearer in what I'm doing, showing it to you. Okay, so we've got three substances that we're going to be working with, and we're going to actually mix them together. We're going to find out that when I mix these three things together, sodium bicarbonate or everyday baking soda, and I have some of that right here. There's my baking soda. And then I also have some calcium chloride. We're all familiar with calcium chloride, given you're from Minnesota and I'm from Michigan. This is our famous road salt that we put on our streets so that we don't slip and, so it melts it lowers the melting point of the ice so that it melts at a lower temperature. That's calcium chloride. And I also have some sucrose. And I have some room temperature liquid water. First thing I want us to do, I'm just going to report the solubility of each one of these just because of the situation. Normally we would just do this ourselves. But both road salt is fairly soluble. It's calcium chloride, a very soluble substance. So it dissolves fairly readily in water. So we should just mark that down. Sugar or sucrose, plain everyday sugar, is also very, very soluble in water. And baking soda is fairly soluble. I wouldn't say it's 100% soluble. It ends up looking a little bit cloudy when you dissolve it in water. Like if you take a teaspoon and stick it in 10 to 20 milliliters of water, but it's fairly soluble. It certainly doesn't say as a solid, a light suspension maybe. So those are our observations that you should write down. And what I'm going to do now is I'm going to combine all three of these things together. I'm going to actually take a fairly heavy Ziploc paper bag to do this. And what I'm going to do is I'm going to actually move my phone so I don't ruin my phone accidentally. And I'm going to do something very important to do that I forgot to do. I'm going to put on my goggles. It's really important anytime you do an investigation to put on your goggles. You never know what's going to happen. I've done this lots of times. Seems fairly safe, but you never know what's going to happen. So I am going to take, so once again, I want you to look at this is my road salt, my calcium chloride. I want you to look at it. You see it's a white solid. It actually is little round kernels. I don't know if you can see that, little tiny round granular things. That's what it looks like. I'm going to take a tablespoon of it. And I'm going to put it inside my bag. And then I'm going to take a tablespoon of the baking soda, and you'll see it's also white powder. It's a little bit different in that it's really finely, it's really very fine. And I'm going to take a teaspoon of that as well. And I'm going to put it in my bag as well. And I'm going to mix them up. And when I mix them up, nothing happens. They just get mixed up. So putting solid sodium bicarbonate and solid calcium chloride doesn't do much of anything together. So now I'm going to add a little bit of sugar, or sucrose. It also is a very fine white powder. Unless you taste it, it's a little bit more fluffier, but pretty hard to distinguish from baking soda, although there are some differences. I'm going to take a tablespoon of it as well. And I put it in my bag. And again, I'm going to mix it up. And nothing much happens. Now what I'm going to do, just put my bag down for a second. I'm going to move my keyboard. I have just some water. And I'm going to take about 10 milliliters. So I don't know if you can see it. I'm up at 50. I'm just going to go down to about 40. So I got it down to about 40. I don't think you can see it, but I got it down to be about 40. I got about 10 cc's in here. You can put more if you want. You'll see my caution in a second about why I don't want to put more. Now there's my bag, right? And what I'm going to do is I'm going to carefully take my bag, my water, and I'm going to place it in my bag without spilling it yet. So I'm going to put it on the bottom, and the water is just sort of on the bottom there. Everybody see that? So I now have in my bag a mixture of sucrose, baking soda, and road salt, and they're all mixed together, and there's the water in the cup, but they're not mixed. Now what I'm going to do is I'm going to try to get as much of the air out of this bag as possible. All I'm doing is I haven't mixed it, I haven't added the water yet, and then I'm going to seal it and make sure it's nice and tight. Okay, so you see I made it nice and tight. You can also see, hopefully, the bag is a little puffed out here, but that's because of the container that I have in there. You can see that the bag is fairly flat. Now I want you to make a prediction of what happens when I now tilt the water into the bag? What's going to happen? So I'm gonna do that. I'm gonna now, everybody can see my bag. I'm now gonna tilt the water into the bag. I'm gonna just mix it up a little bit. And nothing wants to happen this morning. Well, that's pretty weird. There we go. So I don't know if you can see that. Everybody see what's happening, I hope. If you can see what's happening, add it to the chat. What do you see? Okay, so I'm going to just let that there for just a couple of minutes. And why, okay, I see Danielle is saying that I see gas foaming in the bag. Kevin says bubbling. Cheryl says bubbling. And why we let this just react for a little bit, I'm going to answer Kevin's question. I'll keep holding this up. Kevin said, would you say that inquiry has represented in science instruction has been replaced by practices? I would say that practices more finely define what inquiry is. So it's not that it's replaced it. It's just that it's enhanced it. It's defined it more. It's been more specific. So when we say engage in inquiry, in the past, it was always a little bit, what did that mean? I guess it always meant that kids would do an investigation or do some kind of hands-on activity, but it didn't necessarily mean that kids were figuring out, that kids would construct a model, or that kids would write an explanation with evidence. And so that's the difference, right? It's not that inquiry is gone. It's just that it's more fine. The notion of practices and engaging in practices is more finely defined. What does it mean for engaging kids in inquiry? As I said before, asking question was always a hallmark of science teaching and learning. We'd have this crazy list of 8 things or something, right? And the first thing was asking questions, but kids seldom ask questions. And one of the things that the practice is trying to do is to bring kids back into asking questions and not just carrying out a procedure. And so it's more tightly defined. So I think if you look at my bag right now, I think you can see a couple of things. If you notice my bag, remember it was flat before? And a lot of you said I noticed bubbles or gas being formed. You'll notice that the bag is now puffy. And I can show it, I can squeeze it together and you'll see that it's puffy, right? So it's not, so something was formed because it's certainly taking the place, the space that was in this bag. It pushed it out, right? The other interesting thing is you're not going to be able to do this, but it feels extremely cold, right? So if I touch the liquid, if I touch this down here, it feels cold. The other thing you might notice, and it's a little hard, you'll notice that whatever I formed, whatever's in here now, isn't necessarily 100% soluble. I think you can notice on the bag right here, this kind of cloudy material, right? We call it a precipitate. This cloudy forming stuff. And so we see some indications of something happening, right? It felt cold. The bag became puffier. It's actually still getting a little bit more puffier, right? You can see that puffiness, right? It's cold. I can see this cloudiness. In fact, if I would have made 2 of these, I didn't think of that. We would see something happening. Now, what I'm going to do is I'm going to call my handy dandy assistant. Hey, assistant. Well, I thought I had a handy dandy assistant, but I guess I don't. Here comes my handy dandy assistant.
Oh, I need to get my documents.
Okay, well, so what we're going to do is, again, I want you to make a prediction once again about, I'm going to actually open this bag up and I'm going to have my assistant open this bag up, and I am going to put a match in it. And I want you to make a prediction about what you think is going to happen if I put a match in it. What would happen then? And I guess the first thing I'm actually going to do, though, is I'm going to show you something else. I'm going to take a very similar plastic bag, came out of the same box, and I'm going to have my assistant just open it up, and I'm going to put a match. So just a plain plastic bag that I just opened up, and I'm going to my assistant here, my wife of 41 years, is going to help me out here. Can you hold the bag in?
Oh, sure.
Ann's actually a science teacher as well. And you're going to have to hold it up so they can see the screen. Great. So I want you to make a prediction. When I put the match inside the bag, and the bag has air in it because that's what's in it, I want to know what's going to happen. So I think I here's my match, and I'm going to put it in my bag, and you'll notice it just keeps burning inside that bag.
Oh, I don't want to get burned.
Okay, you won't get burnt. So now we're going to take this bag. Again, here it is. This is the one that we've been using. And you'll notice, again, it's puffy. I'm going to ask Ann to open it up. Make a prediction. What's going to happen now when I'm going to put it in the bag, in this bag? Oh, hold on, Ann.
Went out.
I know.
Late, kind of started.
That's okay.
No.
Okay, here we go. Ready? I want to get it lit. Okay, everybody can see the match burning. I'm going to put it inside the bag. And what does it do? It went out. So it's there. Whatever inside this bag, or whatever was inside this bag, there's still some of it inside that bag, reacts very differently. Thank you very much.
Okay.
Reacts very differently than what was inside this bag. Right? So we see a couple of things. We see this was cold. We see that the bag became puffy. We actually see all this cloudiness. A really cool thing to do if you want to do this little experiment is also actually hold it on the side like this, suspend it inside another glass for a couple of minutes. It'll do, and I'll show you in a second. And you can actually see more clearly this precipitate. You see this sort of the solid stuff coming out. So I'm just gonna take it. Everybody see that right now, the way it looks. I'm just gonna take it. I'm gonna put it down for a little bit, and then I'll come back to it. Okay, so what we're gonna do is I'm gonna take out my goggles. I don't need my goggles on anymore. I'm gonna actually just take a second and put the lids back on all these solids so that I don't spill them. And I will answer Kevin's question, who basically says it's interesting to me that inquiry wasn't really referenced in NGSS. Yeah, it is interesting. I believe it was referenced in the framework, not too often. And, Kevin, the reason why, or everybody, the reason why is because inquiry, the obvious, it's very important. I've been engaged in trying to get classrooms to do inquiry and myself doing inquiry in my own teaching since 1976. But one of the concerns with inquiry is that it kept to be meant everything from kids following a step-by-step procedure to kids sort of designing their own investigation, to kids doing just a one-day activity, to kids doing a long-term activity. And so it just had too great of a variety of meaning. And so the whole notion behind the framework at NGSS was to give it more specificity and to say, if we're going to engage kids in inquiry, what is it that we have to do? What should we do? And that's why the scientific practices are there. Okay, so what I want you to do right now is again, if we were together, I would actually have us write a scientific explanation in teams, but we're not. So I'm going to ask you to write a scientific explanation on your own. And I will ask you to share by typing some things into the chat. If you don't feel comfortable, it's okay. But hopefully some of you will be able to share. And so the question that we were trying to examine is basically, did something form? Did I form something new when I combined the baking soda, the powdered sugar, the rolled salt, and the water? Right, so that was my question. All scientific explanations always respond to a question. And if you remember correctly, here was my question. When you mix substances together, how would you know whether new substances are formed? In our particular case, we're interested in when I put together baking soda, powdered sugar, rolled salt, and water, did I form something new? So a scientific explanation always includes a claim. And that's a statement that responds to the question by relating one variable to another variable. So it's not just saying yes or no. It's saying it's relating the variables to one another. That's the first part of an explanation. The second part is evidence. And evidence is your data that's in support of the claim. So there could be some irrelevant data that might not be valuable. But in fact, it's the data that really supports the claim you're trying to make. So it's appropriate, but you also need sufficient. And then there's reasoning. Reasoning is probably the hardest aspect of any scientific explanation. It doesn't matter if you're a middle school student, a high school student, a college student, or a university researcher, right? It's really saying why the evidence that you have supports your claim. And the only way you can do that is by using the scientific ideas, the big ideas. So reasoning is the process where you actually apply your science knowledge to answer the question. So I want you to write the scientific explanation, but I also want you to write any new questions that you had that came to mind as a result of doing this investigation. Did you have any other questions? I asked the question, I started asking the question, did new substances form when I combined baking soda, powdered sugar, rolled salt, and water? Well, what questions do you have now? And so that's what I would like you to do. So I'll come back to the slide in a second, but I just want to state that scientific explanations are critical to science teaching and learning, but they're also critical to science. It is the underlying aspect of what science is all about. Science is all about explaining phenomena. That's what we're all about, and what evidence that we have for supporting it. It's key to the next generation of science standards and the framework and investigation and design. And the reason why is because it can really promote students' image of science. It takes the notion of science being a list of facts or a list of ideas to some place that can take the kids understanding the world in which they live. Why did that phenomena occur? So it enhances their image of science. It enhances their understanding of the nature of science, because kids come to realize that if I need to make a claim, I have to have evidence behind it to support that claim. And it fosters, because I'm using my ideas, it fosters deeper understanding of important ideas or the big ideas of science. So I want you to I'm going to give you like 4 or 5 minutes, and I want you to write a scientific explanation. What's your claim? What's your evidence? Remember, a claim responds to the question by relating one variable to another variable. You get your evidence and you get your reasoning. And if you can come up with a new question, you can. I don't know if you can see this. Yeah, it's not going to come out in video. Anyways, if you saw this right now, if I'm looking at it, you'll actually see a beginning of a separation where there's a clearer layer at the top, right about there. It's only about maybe 1/4 of an inch. And then you'll see a thicker solution because stuff is starting to settle on the bottom down here. And of course, you can see on the side of my bag here, all this white stuff. So I'm going to leave that as part of our observations that we made. And then I'm going to just give you 4 to 5 minutes. And once again, I'll find my phone and I'll start my phone. I want you to write. I see Danielle also, she beat me to the point. My goodness. Okay, I'll give you guys 3 minutes to write your scientific explanation. Then we'll come back and we'll critique Danielle's, if that's okay, Danielle, because the whole thing is what's the claim? We're going to critique our explanations. What's the claim? We'll hear what other people have to say about it, evidence and reasoning. So I'll just give us a couple of minutes to sort of do that.
I think I'm going to screen else.
What?
I'm going to school.
Okay. Okay, so that's about 3 minutes. And I do see a couple of, I do see a couple of responses. And so I'm gonna stop my watch and I guess, Danielle, do you mind if I guess you stuck it up there, so I guess you don't mind, since you're the first to put it up there. Do you mind if I use yours as an example? And she says, not at all, thank you. But we'll also refer to Kevin's and the other document as well. I think everybody can see Danielle's response, and we're going to look at it piece by piece. So you'll notice that it says new stuff. Her claim is new stuff is formed when baking soda, powdered sugar, road salt, and water were mixed. Right? So the question is, that's her claim. And does she write an appropriate claim? So the appropriate claim is, a claim should respond to the question, and it should relate one variable to the other variables. In this case, I'm going to give everybody a second to think about that yourself. Did she do that? In her claim, new stuff is formed when baking soda, powdered sugar, and rolled salt and water were mixed together, Did she answer the question? And then she relate one variable to another variable. So I'll just give you 30 seconds to think about that. What kind of feedback would you give her if she was your student? And then I'll give you my comments on it. So I would respond to yes. Danielle did write a claim that responded to the question, and she did relate variables to one another. So the variables she related were the inputs, the baking soda, the powdered sugar, the rolled salt, and water, did form new things, which was the output. So the final thing, right? So the input variables were the independent variables, were the four substances that we put in the bag, and the dependent variable was the outcome, which is was new stuff formed. I don't know if that's clearer now, but the layer at the top is actually becoming, you can see a larger layer at the top, but it's also becoming thicker at the bottom. We'll come back to that again. So I think that's great. Let's go and look now at her evidence, right? The second part of any explanation is her evidence. So her evidence is when the four substances were mixed together, the temperature dropped, the bag filled up with gas, and the mixture became cloudy. So is that evidence? And I'm going to respond. I'm going to pop back down here a little bit. To look at, I think Kevin added more evidence to add Danielle. New substances may have new levels of solubility, but not sure, right? So Kevin is saying that that's the cloudiness part, that if a new substance was formed, that they're probably not as soluble, because we know, although we didn't do it firsthand, I reported that the sodium chloride, the sodium carbonate, the baking soda, the powdered sugar, and the rolled salt were all fairly soluble. We're actually all baking soda and powdered sugar are very soluble. Rolled salt and powdered sugar are very soluble, whereas rolled salt is fairly soluble. I think you can see this now even a little bit clearer, that there's a liquid layer on top. See that little liquid layer? And on the bottom, there's a much cloudier, thicker layer. If you actually leave this for an hour, it really settles out nicely. So that's our evidence. I'm going to go back up here just a little bit, and I'm going to look at what Cheryl has to say. A gas was formed when the three things are mixed. So gas is formed is certainly evidence that something new was formed. Why? Because there wasn't any gas there beforehand, right? That's why it was so important to squeeze everything out of the bag, right? To show that there's hardly any gas in here. And when I mix these two things together, this gas evolves. So all of us have this notion that a very convincing part of what's going on is a gas was formed. It wasn't there before, and it's there now. So we've got this the gas, the box, the bag filled up with gas. and that the stuff that's formed, we think it's a new substance because now the stuff that's there isn't as soluble as the stuff was there before. And now let's go look at the reasoning. I'm going to just talk, just so that you know, and as a chemist, you just please realize I've been trained as a chemist. Interesting enough, temperature changes can be caused by anything. A chemical reaction or when new stuffs are formed, you can get a temperature dropped, but it's not convincing evidence like the gas being formed. The reason why is you can just take materials and dissolve them in water and you can change the temperature. It either gets hotter or colder depending on what the substance is. So dissolving can actually cause a temperature change. So it's not convincing or it's not strong evidence. It's not strong evidence, right? Like the gas filling up, like the solubility, like these things not being as soluble anymore. So let's look at our reasoning. The new stuff formed a chemical reaction. Now, we didn't mention the chemical reaction, right? We were talking about the new stuff happened. Now, you're science teachers, so it's hard to avoid these, what you know already. So that's okay. But with a kid, it's like, did I form new stuff? Because actually, so we'll take that as new stuff, a chemical reaction that occur. And the reason why she's stating is it has different properties than the original substance. That's this piece of science knowledge that you're trying to get kids to apply. That the stuff that we have now, the stuff in this bag, has different properties than the stuff we had before. That's an application and of an idea. And when you get different properties, you know you have different stuff because properties uniquely identify something. Now, this activity was actually taken from the iQuestion materials, and it actually what leads into a definition of a chemical reaction, right? So if you just heard what I just said, when you mix old things and you get new things and they have different properties, that's a definition of a chemical reaction, right? So you take your reactants, they form new products with totally new chemical properties. That's a macroscopic definition of what a chemical reaction is. So that's what a scientific explanation is. And one of the things I love about, if we go back to this, about why it's so important, is that it does help kids understand that science is all about figuring out. It does help them enhance their image of science. But the other wonderful thing about getting kids to write scientific explanations in your classroom, it actually supports their literacy. It gets them to write. And writing and being clear in their writing and explain what they're trying to do is such a critical part of today's world. You can't get a decent job if you can't write. And our children in our schools need to know how to write. And unfortunately, we tend to separate writing into language class, literacy classes, like English language learning, and not in the science classes. So I really love applying scientific explanations to classrooms, science classrooms, because it really supports them in developing strong literacy skills. Okay, I'm going to stop there just for a second. One of my goals for today is to see if you understand, get you to get a little bit of understanding of what a scientific explanation is. So if you have any questions on scientific explanation, please write them in the chat. I can try to answer anything about a scientific explanation. Okay, I don't see any questions showing up, so I'm going to go to I'm going to move forward. And the question I'm going to ask you now, and again, please write this in the chat, is did this activity this experience, let's call it an experience, engage you in three-dimensional learning? Did you use all three dimensions to make sense, explain, figure out a phenomenon? That's what I'm asking you. So take a minute, reflect on it. And did I in fact engage you in using all three dimensions of scientific knowledge? Okay, I see one response in the chat, two responses in the chat now. And there, it also sparked a little bit of emotion, right? I mean, and I'm responding to that because Jen said, because it was fun trying to figure it out. And actually sparking emotion is actually critical in learning, right? So sometimes learning can be really a lot of hard work, but we might be really enjoying ourselves. So we think it's fun, right? That's what you really want to have happen. You really want to sort of get kids to really feel like this is really, I'm really involved in this. So I'm not going to tell you, I'm not going to answer this question. Actually, I'm going to let you think about it yourself. In fact, if they're not, I did, but I'm going to take us through a little activity. And the activity I'm taking it through is right here. And so the question becomes, what disciplinary core ideas, cross-cutting concepts, and science engineering practices did we use to make sense of phenomena? Well, at the very least, I think we all know that the scientific practice you took part in was writing a scientific explanation. You tried to figure out, did this happen? So this is actually from the next generation of science standards. These are the three dimensions. And so it's constructing explanations and designing solutions. But in fact, you did do this. You did construct an explanation and you did design a solution. But in fact, you also analyzed and interpreted data. That was critical for doing this. We could have never, ever written this scientific explanation if you didn't analyze some data, what you had before and what you have now, right? It was qualitative data, right? We didn't do anything, we didn't do any quantitative measurements. We certainly could, if you're in high school, we could turn this into a very quantitative experiment. But from a qualitative perspective, it works nicely too. So we analyzed and interpreted some data as well. We constructed an explanation, we analyzed some data. You may have engaged in an argument. You may say, I'm not convinced yet that this is a chemical reaction. And I actually ask you to ask some questions. And I did get a couple of questions in response, looking back at my notes here. Sorry, forgot about that part. I got a question about what would happen if one of the questions that was asked was, what gas was formed? And we could try to get some known gases and compare it to how it reacted to the bag, right? We could get some oxygen, we could get some hydrogen from little cylinders, some carbon dioxide from little cylinders, and see how it reacts based upon those gases. I also got another question here about, will varying the amount of water added increase the amount of solids dissolved or not? So again, we can see this is actually becoming clear. I hope you can see the white layer of the clear layer, somewhat clear layer of liquid at the top, and then the bottom becoming a thicker precipitate, a thicker solution. If we keep doing this, it'll get even more so. So if I added more water, would that dissolve the stuff more? So those are the questions that we got. So I got you engaged in asking questions as well. And of course, the 2 disciplinary core ideas that we were involved in, which is critical to actually understanding this, and hopefully children's understanding would become richer, is that each pure substance, powdered sugar, road salt, and sodium bicarbonate, has characteristic properties that allow you, and chemical properties that actually allow you to identify them. Right? So putting a match above the powdered sugar or the road salt or the calcium chloride, the sodium bicarbonate would not put out a flame, right? So there's the thing that I formed at the end, that gas that could put out a flame, that's a new property. And in fact, it's a new chemical property because it put out a flame. So one of the disciplinary core ideas is that properties can identify substances. But the second disciplinary core idea that we involved in was that substances react chemically in characteristic ways. Now, we didn't get to the second part, right? That's to come later in our teaching episodes of figuring out why is it that this happened. And the reason why that will, as we keep going in our explorations, it's because the atoms and the substances regrouped. But we weren't there yet today, nor did I ask you a question that sort of lead us in that direction. Then the question becomes, did we engage in any cross-cutting concepts? Well, we could have, if we were doing this together as a group, we certainly would have looked for patterns to see if our data was consistent across the groups. Do all of us form, did all our bags become puffy? Did all of our bags put out the match? Did all our bags actually form these layers of materials? But we can also think of that we use the idea of stability and change, right? So in the beginning, the materials before I put the water in it was very stable. There's nothing happened to those substances when I mix them together. When I put the water in, we see some change occurring over time. We could also say that this had something to do with structure and function. What did the different structures of the materials have to do to cause some of the observations that we saw? Cause and effect. What caused this stuff to happen, right? What was going on there? So you can use this to make a decision. Did I engage you in 3-dimensional learning or not? So once again, linking back to the science and engineering practices, these are the multiple ways of knowing and doing that science and engineering do. And I tried to show that the practices work together. We ask questions, we carry out an investigation. We did not, in this case, use mathematical thinking, but we did analyze and interpret data. We did develop an explanation, although we didn't construct a model. And we weren't involved in any arguments because we weren't working together, but hopefully it also led to some new questions. And it led to some questions and us obtaining and evaluating some new information. So let me just bring this out. So this, I like this little summary kind of slide, because to me, it recognizes the figuring out process. And the figuring out process is driven by phenomena that is so key in the work we do. And it helps to create optimal learning environments. If we can pick phenomena that can engage kids and surprise kids about what's going to happen, that's what drives the process. And it creates these moments. The kids will say, what's going on here? So kids always experience a phenomena. And again, phenomena are events in nature that we can observe, investigate, and then try to explain them. In this case, the phenomena were these 3 solids that we mixed together and then added water. This raises questions. Students can ask their own questions, like what happens when I put these things together? What happens if I add more water? What happens if I leave out the sodium bicarbonate? Was that really important to this reaction? What about the sugar? Was that really necessary? Right? This leads us to using scientific explanation, scientific practices, doing an investigation, developing a model, constructing explanation, analyzing data. That then leads us to figuring something else new, right? The thing that we learned new today was that I form new substances because they have different properties, which is really critical, right? And it also gets us to ask new questions. So I like this. To me, this is the figuring out diagram, which is so critical for three-dimensional learning, and it's driven by the experiencing of phenomena. Sort of another visualization to help us see what's going on in the figuring out, making sense using the 3 dimensions. So in the center, it's what all science is driven by. It's asking questions, experiencing a phenomena, or experiencing a problem. And in order to answer that question or to make sense of that phenomena, I have to use science practices. On the left, I also have to use the big ideas that go across the disciplines. Those are the cross-cutting concepts that are in green. And on the right, I have to use the big ideas of the disciplines. Those are the disciplinary core ideas. I actually like the word big idea over disciplinary ideas because to me, the big ideas is something that there's a lot of ideas in science, but it's the big ideas or the disciplinary core ideas that are so critical. So looking at what we just did, where does this stuff come from? Where does this new stuff, where does new stuff come from? Can I make something new from it? What did I have to do? Well, we asked some questions, we collected some data, we interpreted that data, we developed an explanation. In order to do that, we had to use some cross-cutting concepts. The flow of energy and matter, that was the notion of it becoming colder or hotter, stability and change. I did have this all involved in the system. I really didn't talk about it. So we used some cross-cutting concepts, and then I also had to use some disciplinary ideas. In this case, it was the structure and properties of matter, how matter reacts, conservation of matter, energy transfer, and chemical processes. And here's actually a real world question that I had. I became a honeybee collector, a honeybee person about 5 or 6 years ago. And when I first got my honeybees, all my honeybees died after the first winter. I got wonderful honey from them, but after the first year, all my honeybees died. And and there's thousands of bees in any one hive. And of course, so you feel sad to see the collapse of a hive. The question is, why did all my honeybees die? And so again, I had to find out some information. I asked some questions. I collected data. I tried to come up with models to figure all this up. But just using those ideas wouldn't help. I used ideas of systems, like here's my systems, what's going on, right? The idea of like, did they have enough energy, food, or that's the energy, right? Like what's going on here? And of course I had to apply some big ideas, disciplinary ideas as well, about the interdependent relationships in the ecosystems. Like for instance, was something else going on in there that really caused my bees to die? One possible explanation, for instance, is they just ran out of food. Well, that's their honey, right? Bees make honey to store them for winter, so they actually have enough food. But my hive had enough food in it because I was able to collect some delicious honey at the end of winter. So it wasn't the lack of food. Another possibility was they froze to death. Why? Because maybe I didn't have enough ventilation in my hive. And so because I didn't have enough ventilation in my hive, bees are like any organism, they respire. And when they respire, they give off water. And that water actually collects at the top of the hive and can drip back down, and it can actually land on them and they freeze to death. Is that what happened? And so, you know, I checked the amount of food they had or the end of flow of energy. I checked the notion of them freezing. That wasn't a solution. So they died the second year too. And then I had 3 hives, so it was sadder. And then by doing some more reading and talking to some other bee collectors, I realized there is this organism that can cause them to perish called virula mites. And there's a variety of ways to get rid of virula mites. Some are more organic and some are less organic. I couldn't do the non-organic methods, so I had to use the organic methods. And I'm happy to say after 5 years, I finally got my hives to survive. I had 3 hives that survived. I was very happy about that. This year I added another 2 hives because I'm getting a little confident about myself. And so in order to figure out how things happen, you have to apply this stuff. So just to sort of connect some parts together, experiencing phenomena in the world, in this case, honeybees and what caused the honeybees to die or not, or the chemical reactions thing, those are all phenomena. The reason why phenomena are so critical is because they create this sense of wonderment and curiosity. What is going on here? And it drives our learning investigations. It helps us make connections to our world. And there's implications about this stuff beyond just the world of schooling. So phenomena is truly, and asking questions, experiencing phenomena and asking associated questions is truly critical for kids to engage in 3-dimensional learning. The experiencing phenomena and three-dimensional learning is also critical in building a scientific disposition. And what that scientific disposition is thinking like a scientist, right? What do I need to know here? I wonder what would happen if. How can I explain? Do I have enough evidence to provide to support my claims? Those are all ways of thinking like a scientist. Now, I don't want every kid to become a scientist, because we'd live in a pretty boring world if we were all scientists, because there would be no one to cook us a delicious meal. I think I went out for my first restaurant at one of my favorite restaurants in Ann Arbor, and it was great. I'm a good cook, as I said, but I can't cook some of these things that I eat when I go to restaurants. So we need good chefs. I also love art, and we need people who can create art. I love music. I love to listen to music. So yeah, science is one field, but there are all these other wonderful fields. But every one of us need to be able to have a scientific disposition to wonder about the world and wondering about what's happening. So here's my dream, the sort of wrap. I got a couple of questions. I think I'm gonna go look at my questions or comments there. Right, so there's 2 good comments here. If you haven't looked at them, you might want to take a look at them. One is from Danielle, and she says that one of the important aspects behind phenomena or phenomena-based learning is that it gets the kids excited. Absolutely, right? You got to pick phenomena that really are complex, but are also compelling to kids. And what it does is that they take it home and they talked about it to their parents and their family members, as Danielle points here. So it's really critical. Kevin answers that what's part of, if you go back to my diagram as far as cooking, to make, you not only need the practices and the spices and the main ingredients, but as far as phenomena-driven science, picking a good phenomena is really critical. So maybe it's like picking the great dish, right? Maybe the phenomena is the dish. And so you have to pick the right dish to really engage students. And then someone said here, I can change I don't think I have control over the system. So you're welcome to change it to attendees, and they can add comments if you like. That's probably a good idea. I can see if I can do that. Yeah.
It's okay, Joe. You don't have to do anything. I had mentioned it a few times in the chat that if everyone could change in their chat the to line where it says two panelists and make it two panelists and attendees, because some of you are chatting and only Joe and myself can see what you're chatting and the attendees cannot see it. So
Oh, I didn't realize that.
yeah, and you know, I missed announcing that at the very beginning, but I was chatting it and I thought we had everybody covered. But I do see Kevin was just chatting to attend or to panelists only.
Well, I apologize. I thought everybody could see the chat. I hope it was worthwhile for everybody. Anyways, here's one of my dreams. And it's the notion of engaging all students in explanations K through 12. Because if we could engage kids in constructing scientific explanations throughout K-12, just imagine the different kind of learner we would have. We wouldn't have individuals out in the world just accepting any claim. And part of that is when you go to a doctor's office, right? I mean, I highly respect doctors, and I probably wouldn't be here today talking to you if it wasn't for doctors. But we have to be somewhat skeptical of everything they say to us and check out what they're saying. We just don't want to believe their claims. Same thing with all the, is it really better to spend $8 for a box of eggs? Or is the $2 box of eggs just as good for us? What's the difference between an $8 box of eggs and a $2 box of eggs? So we're always reading claims all over the place. And what's the evidence for that claim? And we have to realize that evidence changes all the time. And that's part of what it means to be being a scientist. And so if we can get kids from the earliest grades on, writing scientific explanations based upon them collecting firsthand data and making sense of that firsthand data. Again, it's showing how the practices all work together. We will just have a different type of learner. And the critical aspect here is that if they didn't do it in K2 and then K3-5, then when they're in middle school, it's going to be harder for us. But if middle school teachers can build off the experiences in which third graders are actually using evidence to construct or support an explanation, then when they get to us, we can really talk about what's really valid and reliable evidence. And we can push writing scientific explanations that much farther. Similarly, if us as middle school teachers really focus on writing explanations, when they get to high school, the high school teachers can push them that much farther. So it's really critical for us to always focus on helping kids write an explanation, because it's such a critical aspect, such an important part of what science is all about. I like to have I got this little idea from my colleague, Christopher Harris, who's now at Wested. And the notion is that the 3 dimensions bring a different perspective to classroom instruction and assessment. And that different perspective is that the focus is on kids making sense of phenomena, figuring out phenomena, or finding solutions to problem using the 3 dimensions. It's actually engaging them in scientific practices, using disciplinary core ideas and cross-cutting concepts. It's a very different way of organizing instruction than we did in the past. So I'm going to give you a minute to write a takeaway. And I'll read all the takeaways that actually come on into the chat so that you can see them. And then I'll show you some of my takeaways. So I'm going to give you a minute to add what was a big takeaway that you had from today's session, and then I'll share my takeaways with you. So if you could just take a minute, I'll go back, put my phone on so we have a good minute, and then we can move forward. So take a minute. What's a big takeaway from today's session? Okay, I'm gonna stop my watch and I'm gonna go look at some of these, and I'll read them because I don't know if you guys can see them or not. I'm actually gonna start with this one that Danielle wrote. It was before I asked this question, but it really applies. And I don't know if you can see these in the chat, so I'm gonna actually just read them to you. So this was one that was actually came up before I asked this question, and it says, to be a good science learner and thinker is like having the cooking skills to put all the pieces of learning together. Right. So it's really important that you use everything. It's not just knowing the content. You can know lots of stuff, but you can't figure something else out new because you don't have the practices to figure something out new. And this then comes to Danielle responding to my question. She says, all three dimensions of learning are important and used appropriately in a well-planned and well-received lessons, right? So if you really want to get kids to use their knowledge, we got to get them to use all three of those dimensions in really appropriate learning experiences. Let's go back. The next one is from Jen. And it says, while not all students will become scientists or engineers, all students should be exposed to three-dimensional learning experiences so they're able to make sense of the world around them. That is very true. And even if you just want to be a hobbyist, and how can I get my sunflowers to grow bigger, and what's needed. So we want all students to all students have to have a basic level of scientific literacy to exist in this world today. And I think the last year of the pandemic has really shown that, with just a lot of confusion about how the disease spreads, what's it going to take to go away, et cetera. Patsy, first time I'm hearing from Patsy today, so welcome, Patsy. And she says, I love the idea of having students write a focused explanation. Yeah, I think it's really critical too. I can't agree with you more. Cheryl writes, encouraging curiosity, students to ask questions. Yeah, it's so critical. It's really kind of interesting. The easiest way to get kids to ask a question is to have them experience a phenomena and just say to them, ask a question, right? Part of the reasons why kids never ask questions anymore is we never give them the opportunity to ask questions. Of course, we have to work with them to shape it to be a stronger scientific question, right? In which there actually has variables in there, but we can do that. All we have to do is show them a phenomena and ask them to ask questions. They can do it. Kevin writes in response to the takeaways, NGSS doesn't represent an additive approach to PD, professional development, teaching, learning, etc., but a truly transformational approach. This is correct. You'll see that. I agree with that 100%. It's just doesn't, it's not adding something. It's different. It's revolutionary. It's not evolving. It's very different. It's revolutionary. It's transformational. I like that term better. Despite the fact that NGS has been with us for a while, 8 years, we have much work to do. I couldn't agree with Kevin more. We've made some progress, but we have to keep pushing. And that was all the takeaways that were put in the chat. And here are my takeaways. Three-dimensional learning involves, it should say involves students in figuring out, making sense of phenomena. The ideas of three-dimensional learning are critical for principled science reforms, right? It's all about what science is all about. And then the last one, engaging learners in making sense of phenomena using three-dimensional learning creates optimal learning experiences. This is actually relating back, I believe it was to Danielle's first comment or someone's comment, that it really gets kids excited and want to go home and talk about stuff. That's an optimal learning moment. When kids actually feel, even though it's hard work, they actually feel pretty good about doing things. So looking back at the framework for K-12 science education, the next generation of science standards, and investigation design at the center, what's different? Business is not the same. Science teaching is not the same. The framework is different. NGSS is different. We're living in a time in science education that's different. It's revolutionary and not evolutionary, right? It's not additive, like Kevin said, but it's transformational. It's so different. You know, I used to pride myself on being able to give good explanations of content, but it's got to be more than that. It's the kids who have to give the good explanations. It's the kids who have to be able to figure out. I know I can do it. My goal as a teacher is to get them to do it. And that's hard. It's a different vision of what teaching is all about. Anyways, I want to thank Activate Learning for inviting me to do this session. In fact, the activity that you experienced today, the Baggy experience, you know, I think you might be able to see that a little clearer now. You see the little white layer at the top and the thicker, the precipitate layer at the bottom is actually in the 7th grade chemistry unit called Introduction to Chemistry. How can I make new stuff from old stuff? It's really a wonderful little activity to really engage kids and stuff.